So, angle in standard position. An angle is said to be in standard position when its vertex is at the origin, its initial arm is along the positive x-axis, and its terminal arm is somewhere within the circle. Well, really, what does this mean? And what this is saying is that we have this thing called the terminal arm. Now, when we're looking at this terminal arm, the terminal arm can pretty much exist wherever it wants, but it always emanates from that origin, and that's going to be something that will be really important at a certain point. So when we look at this terminal arm, if we read the angle from the positive x-axis to the terminal arm, that's going to give me the angle in standard position. Now the directional arrow, and when we say the directional arrow, that's referring to these curved arrows right there and that curved arrow right there. That indicates how the angle is going to be measured. If we're measuring from here and going around in the counterclockwise direction, that will give us a positive measure on the angle. If we're starting from here and going in the counterclockwise position, that gives me a negative reading on the angle. Now, what I'm going to do is I'm just going to take a moment here and we're going to quickly talk about the quadrants again, just to kind of give us a little reminder for anyone that's forgotten. If we look up here, you guys see how the quadrants are all labeled. And I have my quadrants labeled where we start from number 1 in what we call the first quadrant. So from 0 to 90 degrees, 0, 90 degrees. And that's quadrant 1. Then from 90 to 180 degrees, we call that quadrant 2. From 180 to 270, we call that quadrant 3. And from 270 back to 360, we call that quadrant 4. You'll notice they're numbered in Roman numerals. That just has to do with they're the least likely type of numbering to be used in any other facet of mathematics because they're so inefficient. And they look really nice. So that's sadly the reason why we've labeled our quadrants with Roman numerals. From there, just remember that if we are going backwards on this, because I'll be referring to this in a sec, but it would be 0, and then here would be negative 90, here would be negative 180, here would be negative 270, and there would be negative 360. And that's if I'm reading those angles in that negative direction. Okay, this is just going to sort of come into play in a little bit when I get to some further questions. Now, example 1. Draw the following angles in their standard position. So let's take a look at this. 110 degrees. If I draw out my coordinate grid right here, again, we go 0, 90, 180, 270, and 360. Well, 110 degrees is just slightly above 90, so we draw it right there. And that gives us theta equals 110 degrees. Just going to turn my pen on a little bit more thin here. That did not work. I'll try one more time, and I will stop wasting everyone's time with this. 1. There we go. Now, theta equals negative 150 degrees. So I again draw out my Cartesian coordinate grid. Now there's two ways that I could view this negative 150 degrees. I could say, well, it's negative 150, so I go 0, negative 90, and negative 180. And then we could say, well, negative 150, a bit closer to right there, and I go theta equals negative 150 degrees. Or, since the entire rotation is 360, I could have gone 360 plus negative 150, which would end up giving me 210 degrees, which, if we go 0, 90, 180, we again see that that matches that angle, and that gives me the same angle of theta equals 210 degrees. 400 degrees, this one gets a bit crazier. So we want to draw this in that standard position. So my 400 degrees means that I'm going to do one complete wrap, right? So 400 degrees, we go 0, which we also know is 360, and it goes around that once. From there, it goes up, and it gives me that standard angle of theta would equal 40 degrees, because 400 is 40 degrees away from 360. Negative 500 degrees. So now again, if we start at that 0 and we go one direction all the way around backwards. So I go backwards and I go backwards to that negative 360 degrees. Well, after that, that's going to leave us negative 500 minus negative 360. That's going to leave us negative 140. So right here, that would give us the negative 140 degrees. Subsequently, if I added that to 360, that would also give me a theta measure of 220 degrees. Now here, we're going to get a bit more crazy in these next ones, because you see we have 3 pi by 4, and we have negative 3 pi by 2. So looking at my 3 pi by 4, well, if I go back, and you could also do this by converting and then reconverting it back in, or as we're going to do it right now, well, 0 degrees is 0 degrees, 180 degrees is pi radians, then 90 degrees is pi by 2 radians, and 270 degrees is 3 pi by 2 radians, or if we get all the way around, we're going to have that 2 pi. So now what we're doing is we're looking for 3 pi by 4. Well, 3 pi by 4 is 3 over 4 pi. That's bigger than half pi, which is pi by 2, but it's less than a full pi, which is pi. So that means my angle is going to exist right in there. And there's our 3 pi by 4 radians. Negative 3 pi by 2. Well, again, if we label our axes off right here, 0 radians, pi radians, and I always label it like this, and then we have pi by 2 radians, and then, sorry, I forgot to put the negatives there, but we go 0, negative pi by 2, negative pi, and negative 3 pi by 2. So this would be my angle theta equals negative 3 pi by 2. Subsequently, since we know the entire rotation is 2 pi, if I went 2 pi plus negative 3 pi by 2, which would give me 4 pi over 2 minus 3 pi over 2, that could also tell us that theta would equal pi by 2. So right here, what we could also get is theta equals pi by 2. So this has just been a brief little introduction lesson. The next thing we're going to get into is coterminal angles, which represent the multiple rotations. I hope you guys have enjoyed.